In this section, I want to look at quite a few different reagents that can be used to react with alkenes and what happens. And the first one that we're going to be looking at in this video is hydroboration. You notice here that I said it's hydroboration followed by oxidation because the net effect of this particular reaction is the addition of water over a double bond. And so we're going to look at that in a stepwise fashion. And many of these, all of these reactions that we're going to be doing involve reagents that are going to be pretty much new to you. The first reagent we're going to be looking at is borane, so BH3. Now, borane, you probably haven't come across this yet. However, it does look very similar to sodium borohydride. So if we added one more hydrogen, that would make it BH4 and it would be minus, and then we'd have a sodium. And we could have obviously a lithium counter ion or as well potassium. That's not very common, but there are those things. And you know those things are reducing agents. Now, borane can actually be used as a reducing agent as well. In the context of our second year course, we don't look at those reactions. But what we do need to know is how borane reacts with an alkene, because it actually reacts very, very well. So if we look at boron, one of the things, I'm going to look at it from the side onwards. So we're looking at it from the side. And one of the things that we should recognize is that a molecule like this must be trigonal planar. If it's trigonal planar, that means it's sp2 hybridized. And if it's sp2 hybridized, there is a missing p orbital. It's an empty p orbital. This molecule is neutral, but we do have this empty p orbital which sits on the boron. And that p orbital, which is empty, is really the thing that defines all the reactions where we have boron. It makes boron a very good Lewis acid because it can accept electrons into that. And that's precisely what happens over here, is that the pi bonds are just at the right energy level, high enough HOMO to react with the boron. But because the boron is connected to these hydrogens over here, when the nucleophile adds to this empty p orbital, we activate it. The boron becomes negatively charged because we just put electrons on. This makes one of those H's effectively a minus, which then back adds to the other carbon over here. So how does this look when we draw it out? Well, the way that we often draw it is something like this. We draw the boron and the hydrogen, and we're not going to worry about the other two. I'll speak about that now. But what happens is the pi bond adds to the boron, and as it adds to the boron, this bond over here, it doesn't matter which one, but the sigma bond raises up in energy, becomes much higher in energy, and it then back donates in one step to the carbon that we have over there. So we can draw this out and see what this looks like. Okay, so this is the hydroboration reaction. What we've done, it's hydroboration. We've put a hydrogen and a boron over the double bond. Notice that it's a syn addition. We've added it at the same time. So this is on the same face. And that's why we know this mechanism is occurring, because if it was, if we didn't get the hydrogen and the boron adding to the same side, then what's likely is there'd be some other kind of mechanism where it adds once and then another nucleophile comes in. But because of this, we know that this must be an addition which is happening at the same time. It's almost like a Lego block kind of clicking on top or on the bottom of the alkene. I've just shown one of those examples there, which means, of course, that this is effectively racemic. Both the H and the boron are either pointing up, or it's the other enantiomer where the H and the boron are pointing down. All right. Now, if you look at this ends up being a little bit more complicated than I've drawn over here. Not to this point. This point is fine. But notice that there's still some more BH bonds over here. And it turns out that this can add another 2 times. In other words, we can take 3 of these to react with just one of those. You could go and draw it out. They become messy molecules because there's going to be a boron in the middle with all these things hovering around, which can look quite complicated. So normally when we do the mechanism, we normally stop at this point over here just to show the next step. Because these boranes that we're picking up over here, they aren't actually super stable. In the presence of oxygen, they can start to break down and form radicals and things like that. So what typically happens is this is only half of the reaction. That's why I said over here it's followed by oxidation. And the next step is the addition of hydrogen peroxide and a base. Normally it's a hydroxide base. So it could be sodium hydroxide, lithium hydroxide, potassium hydroxide. So what happens here? Well, the product ends up looking like this. So this is the product over here. Now notice what's happened here. And we'll look at the mechanism now. What's happened is it looks like the boron has been replaced with an oxygen over there. That's kind of weird. An atom doesn't just change from one atom into another one. So some kind of reaction has occurred there. The stereochemistries remain the same. Notice this over here has stayed the same. I've just removed that H because we don't normally draw hydrogens on. The hydrogen is pointing up. The consequence, of course, is that the methyl group must be pointing down. I can't just draw a line there. If I drew a line there, then I must show the hydrogen to show where it is. Otherwise, there's no stereochemistry. So I've made the methyl group to point down. So it's the equivalent of this over there. So the question we have to ask is, how did this reaction happen? Now, this is not a mechanism that we normally assess on, but it is one that I think you should be able to do. So we'll just look at this in a stepwise fashion. So what happens is, you notice the boron still has 3 bonds to it, 1 carbon and then 2 hydrogens. In the real case, it'll have more bonds to carbons, but we don't have to worry about that for now. And what happens is H2O2 in the presence of a strong base, this deprotonates the peroxide and it generates this over here, the peroxide anion, which is a very nice nucleophile. And that is going to add to the boron. And we're going to get this intermediate sort of peroxy acid. So let's draw that out. Okay, so what happens next? How do we go from there to there over there? That's a little bit more tricky. It's not going to happen in one step. But what I want you to appreciate is that what we've got here, this OH minus, is something that is needs to leave. This bond over here is going to have to break. And if you think about it, what is the best way that it's going to break? If we're going to take the electrons and put them onto this oxygen over there, the problem with that means that the O is going to be short of electrons. Something very, very wrong is going to happen. We're going to end up with an OH, which is positive, that's just suddenly floating off into the solution. That's not going to happen. The most likely thing that's going to happen is that we're going to lose the electrons are going to break in this direction, kicking out an OH minus, which is what we are kind of more familiar with C. Now that, of course, is a very bad leaving group. So this is not something that's just going to pop off and leave like that. There's a reason that it's going to leave. And the reason it's going to leave is it turns out that this bond over here, because we've negatively charged now, all right, on the boron, is actually a high energy sigma bond. And what it wants to do is it's going to move across to bond to this oxygen over there. Notice what's happening. The electrons are sitting in this orbital over here. They're going to move onto this oxygen. That's why this gets kicked out. So we lose that. This bond remains, but this one is breaking. So the net effect of that is that we are going to now get a situation where we've got all these carbons as we normally had. And this is our new bond to oxygen, and then the bond to boron and hydrogen. And now we've got an OH minus over there remaining. So that was the leaving group that left over here. We can color it in green just to notice that. Sorry, I made a mistake here. That should have been a 2. All right, so at this stage over here, we have what is known as a borate ester. And the borate ester, this bond over here is extremely weak because once again, what can happen is we've got an OH minus over there. It can kick in, so we kick onto the boron, and then this can leave, and we leave as an O minus. And all we need to do is at the end of the reaction, there's normally some water and stuff present because of the hydrogen peroxide, etc. So we can protonate it, and it ends up, so normally during workup, we add a H plus, and we protonate it, and we end up with the alcohol that went on over there. All right, so that's the mechanism of this reaction. What's more important with the hydroboration is really just to look at it from a very simple level. It is a way of adding water over double bonds. So look at what's happened over there. It's gone from there to this product over here. We've added an OH on the one side and an H on the other. And now this reaction is often explained in the wrong way. Often people say this. They say that hydroboration followed by oxidation is an anti-Markovnikov addition of water. This statement, though, is extremely problematic. Okay, it's extremely problematic, and I want you to be very, very careful of it. Why they say it's anti-Markovnikov is because if we took an alkene and we added acid and water, so the proton would have ended up on this carbon to get the most stable carbocation over here. And then the water would have added over here. So we would have had OH over there and H would have ended up on this carbon over there. So it would have been the other way around. Now, first of all, the hydration of an alkene under those conditions, so adding water and acid, is terrible. It really isn't one that's going to work very well at all. We've looked at that. The elimination reaction is just as likely, so you're not going to get a good yield. But the whole idea of what Markovnikov's rule was saying is that in that reaction, it favors where the most stable carbocation would be. Now look at what's happening over here. When the alkene adds to the boron, it's adding to the boron, and the boron is going to the place where the least stable carbocation would form. In other words, the most stable one would be over there. So the regioselectivity of this is actually still following Markovnikov's rule. All right. It's just that the product is really kind of like an apparently reversed version of Markovnikov's rule. So we should really put the word apparent here because it isn't anti-Markovnikov. So you'll see this in many YouTube videos and things like that, but it really isn't anti-Markovnikov. In terms of stereochemistry, just watch that carefully. It is a syn addition. There is potential for that to be a point in a tutorial or something to that effect, or a test. But otherwise, this is the hydroboration of alkenes and is a very useful way of introducing an OH over an alkene into the least substituted position of the alkene. Okay, another reaction that I want to look at is an oxidation reaction, which is called dihydroxylation. It's where we're putting on two OHs onto an alkene. Now, there's a very special reagent that we're going to use in order to do that. But just to remind you that there are ways of introducing two OHs, or two hydroxyl groups, onto an alkene. One way is to first treat it with MCPBA to make the epoxide. So that would give us this. So we'd form the epoxide. Notice the stereochemistry. It's a syn addition. All of these things often end up being syn additions, if we understand the mechanism. So we add that. And then if we treat that with hydroxide, nice, good, strong nucleophile, it can come in and it doesn't matter which way it adds to, all right? But it'll add to either side in this case, but it gives us the dihydroxylated product. Okay, so we've done an SN2 reaction over there, and in two steps we've been able to take this and we get this dihydroxylated product. Now notice, of course, that the two OHs are on opposite sides to each other. There is a relationship between them which we would talk about being anti, because they're on the opposite sides as opposed to the term syn, which is where they're on the same side, which is this example over here. So the reagent that we're going to use is probably one of the most expensive reagents out there, but we have a solution. So the reagent is osmium tetroxide. This reagent is incredibly expensive, and it will make you blind if you get it on your hands. So it's quite dangerous as well. However, the thing is, it's actually easy enough to use if we use it in conjunction, but actually just using a catalytic amount of it. So first of all, let me just show you the mechanism of this. What's actually going on? So we've got osmium, and osmium has got the 4 oxygens on it, and it looks like this. And now what happens is, in the presence of an alkene, so I'm just going to draw a simple alkene over here. What happens is, in one step, so this is again a syn addition to this, is we actually get a reduction on the osmium. So this pi bond adds to an oxygen over there. Electrons go onto the osmium. That's where the reduction step is happening. And the electrons over here come back onto the other oxygen there. So it's a syn addition. It's happening in one step, much like hydroboration, happening in one step, much like MCP-BA, adding on one step on the same face. And we get this. And this is known as an osmate ester. So we've changed the oxidation level of the osmium. It was at the 8 oxidation level, 1, 2, 3, 4, 5, 6, 7, 8. All right. And it's now gone to 1, 2, 3, 4, 5, 6. So it's been reduced overall. And what we've ended up is we get this. Now, this thing is actually quite unstable. And so in the presence of water, it hydrolyzes, so just water can go in. This is quite easy. The water will add to the osmium and will kick out. This will get protonated and we get the 2 alcohols. So we're breaking these bonds over here. I'm not too worried about the overall mechanism. What we end up with this is the reduced form of the osmium tetroxide. So we've got an osmium with the 2 oxygens and then 2 OHs. All right, now this reaction over here, so it's really easy to put on the 2 hydroxyls over there. This reaction, however, would be completely impractical if we were going to use this in stoichiometric amounts. Because notice what's happening is that this is the oxidant. It needs to add on. It gets used up in the reaction. This is no longer reactive. It can't do the same thing. And so what we need to do is we need to take this and we need to add something to get it back to the osmium tetroxide. All right. We need to be able to go from the one back to the other. And what we do, it turns out, is a very easy, simple reagent that we can add. It's called NMO. And this is what it looks like. The NMO stands for the M is this one, not that one. N-methylmorpholino oxide. And you don't need, in this course, you don't need to know the structure of this, just to recognize that this is always added to osmium tetroxide reactions because it's an oxidant, which is readily available, very easy. This oxygen over here can be used to reoxidize this, so you get water given off and you go back to osmium tetroxide. So it's really just very useful to know that we can do this dihydroxylations using osmium tetroxide, but it's so expensive that we really want to use this in very, very small catalytic amounts. So the bulk of the reagent is actually the NMO, N-methylmorpholino oxide, which reoxidizes the reduced form of the osmium back into osmium tetroxide. And so this is a very useful way of adding 2 alcohols in a syn addition over a double bond. The last reaction that I want to look at on an alkene is one of the more important oxidation reactions that occurs on an alkene, and it's using ozone as an electrophile. Ozone is quite reactive, and what it will do with an alkene is we'll actually add to an alkene, and we get this a 5-membered ring with 3 oxygens in it. So let's just look at the mechanism, and then we'll kind of work out what the product is, because there's some stuff that's going to be missing over here that we need to add. Ozone is obviously a gas. We can generate it. You can get an ozone generator. We have one in the lab. To be able to do this. It is, of course, toxic to work with, so one does need to work in a well-ventilated environment. So let me redraw this. All right. So I've drawn out the Lewis structure of ozone. It's one of the canonical forms. It's a resonance form that we have over here. 3 oxygens. Obviously, this negative charge can delocalize in over here, and then we get the negative charge on this oxygen. So we've got 2 oxygens with which share the partial negative charge. It's okay. We don't need to draw. We choose one in order to draw out the mechanism. But this is, because of this positively charged oxygen over here, this oxygen, as an example, is quite electrophilic. So the pi bond can add to that oxygen, which is electrophilic, and so this will break. But of course, now what's happened is if you've just added it, so the pi bond breaks again there, but if we just added it onto the one side, this one is now become positively charged, but we've got this negative on this oxygen, which is nucleophilic, and so it can add at the same time. So this is the way we draw out these arrows. But of course, it's what's happening here is something that really happens in one step. This is a picture that we're seeing, but remember, because of the resonance thing, we could have actually drawn this whole thing in the opposite direction. It's a particular type of reaction, which gets studied later on in chemistry. But any event, it is a one-step reaction, and that means, although this is not going to make any difference, it's adding just from the one side. So there's a stereochemical implication, but actually we're going to see later on it makes no difference. So I'm not going to show that, other than to show you that what our intermediate looks like. And this is called an ozonide. And sometimes these things can undergo some other rearrangement reactions. And I'm just going to treat it very simplistically here to show you what happens. Again, this is not an overall mechanism that we often assess at our second year level, but I just want to see, we must be able to recognize how this reagent interacts with alkenes and where we get to. This might feel a bit sort of complicated, but what happens now is that we get another cyclic transition state that occurs, and this bond is going to break. So what effectively happens is that we're going to this is going to kick up over here. This is going to kick out over here, and this one is going to kick in over there. So we're actually going to break a carbon-carbon bond here, and we're going to form a new double bond to oxygen. And this one hasn't broken yet, but we're going to get another double bond to oxygen over here. So let's just draw that out very carefully. So we have this. Notice I've left this bond very carefully. We've got this. That bond broke. This bond is still remaining, and it's sitting as a minus over there. And so this intermediate over here this is effectively, so we've got a positive charge here now. This over here is a type of peroxide, and we need to reduce that. If we leave that for too long, it's going to start doing some really interesting things, which we probably don't want to happen. So we need to reduce it. And this is why I said there's actually something more over here. Normally, it's a 2-step reaction. First we add the ozone, and in the second step, we add a reducing agent. There are actually quite a few different reducing agents that one could use. And all we're going to do in this course is just remember one of them, and which is dimethyl sulfide. So, in the addition of dimethyl sulfide, we reduce, so the dimethyl sulfide will be oxidized, it becomes sulfoxide, dimethyl sulfoxide, and we reduce this bond out, and so we end up with these 2 carbonyls over there. These 2 aldehydes. So ozonolysis is really good. So let's go back to the name of this reaction. It says ozonolysis. Lysis means to break. So we are breaking a bond with ozone. So ozonolysis is breaking a bond with ozone. So effectively what's happening is the alkene is being cut in half. It's been split, ripped open, and 2 oxygens, it's an oxidation, are being placed in that place over there. So this is just one example. Let me give you another one just to see the pattern that emerges over here. So if we're given this question over here, we've got this alkene. What does the product look like? It's ozonolysis. We recognize that. So that bond is going to be cut over there. So all we need to do is to draw out the products, is draw out the 2 bits, and we put the double bond on like there, but now we just put an oxygen on. And on this side over here, we've got 1, 2, 3 carbons, so zig, zag, Here's the 3 carbons, and on this carbon, it's that one over there was where the double bond is. So we still put the double bond, but we end up with the oxygen over there. So the oxygens over here are the ones that end up over there. And what we've done is, in this case, because of the substitution, we ended up with acetone and this aldehyde over there. And ozonolysis is a fantastic way of changing an alkene, opening it up, and getting a reactive partner which can be used, because aldehydes and ketones are very reactive for nucleophilic attack. So it's an extremely useful tool in the chest of organic chemists for reacting with alkenes. Okay.